if you hear it, because there's this intense hailstorm going down. Let's see how that will go. There. Okay, so Manfred was already so nice as to introduce the topic. I'll be talking about global soil water estimates as landslide predictors. And we were asked to point out, because this is the group innovations, what's the innovative part about our research? And essentially that's the global aspect here, because people have been looking into soil water estimates on a regional to local scale. And we tried to now grasp or jump on this challenge of globally. And you already see a hint how we tried to do this. We looked into satellite information, first of all. And there's different satellite products available for different measures of moisture content in the soil. We have the surface soil moisture that can be observed from microwave satellites. And then we have also information on the total water storage within the soil. And of course, both give information about the water content in the soil, which on the one hand can increase shear stress because soil gets heavier, at the same time also decreasing the shear strength, and then both of them leading to a landslide, increased landslide. The satellites that I will focus on today are for this microwave remote sensing satellites that observe the surface soil moisture. Those are SMOS, so the soil moisture ocean salinity satellite, and also SMAP, soil moisture active passive. They operate in a very similar manner, and it's just that one is operated by the European Space Agency and one by NASA. And they have a recurrence time of about 2 to 3 days and a spatial resolution of about 40 kilometers. I know the sounds already very big for landslide research, but let's ignore that for 1 second. On the other hand, we have for these total water storage estimates, we have the GRACE satellite duo. It's the gravity recovery and climate experiment. So they observe the gravity of the Earth and therefore can retrieve some information about the total water content. The resolution here is about a month and 300 kilometers spatially. And already by these definitions that I gave you here, we see some challenges that we face with satellites. First of all, of course, very coarse. I already said that for the 40 kilometers, but of course 300 and a month sounds just very, very coarse again. Also, we actually would like to have information on an intermediate depth of soil moisture content, because that's where landslide geoplanes typically are, not so much in the 5 centimeters and rarely until the bedrock. And then what you see already here, so both SMOS and SMAP are polar orbiting, so their swaths actually always have gaps in between. And that's not only gaps that we do not cover, but generally also there will be at different locations at different time steps. So that means that some time we do not have an observation. To put some numbers to this though, in connection with landslides, we have here now an animation of SMOS satellite observations of surface soil moisture for the time period of 3 months in 2016. You see here in red appearing, those are hydrologically triggered landslides noted in the global landslide catalog. And what you see in blue is that there's a higher surface soil moisture, and in brown it's drier there. And you see now a lot of gray area, more than you might have expected. And that is because those microwave remote sensing satellites, they really have difficulty retrieving soil moisture when the ground is frozen, but also when you have densely vegetated areas, such as here in the rainforest, for example, also where you have strongly urbanized areas and in complex topography. And that's, of course, very difficult if we want to use it for landslides, because that's where landslides occur often. On the right is now an example for the same time period of the GRACE terrestrial water storage with the same landslides overlaid. And again, blue means wetter, brown means drier. And we see now that we have a full coverage. There's not those as many gray areas. And we also see now this lack in temporal change, or we see that the temporal resolution really is a month. So there's not too much change in time, but we do have spatial patterns. Numbers, putting some numbers to this, how many landslides could we actually combine with this data, or for how many landslides would we have had those information? For a study period where we looked at GRACE and SMOS, we found that GRACE was able to actually give information for 75% of the landslides from the global landslide catalog, And you might now wonder why not 100%? Well, the gray satellite sometimes has to recharge batteries, so then a whole month of data is lost. SMOS, on the other hand, we saw already it had way more gaps, and there we had only data available for about 14% of the landslides during this study period. For SMAP, for a different time period, because SMAP only started observing later, we found that we had data available for about 20%, which is better. But of course, if we want to use the information from these satellites directly for some early warning systems or any predictions, this is of course really difficult because you can't predict something if you don't have any data available. And so if you do want data, the next step would be to turn towards modeling, because that's, of course, it gives you a spatiotemporally complete image. And this is now what, at the global scale, you often use land surface models, in our case, the catchment land surface model. It's again for the same time period, and you see now that you have a complete coverage. You see some changes in the daily rhythm, and that's already a great advantage. Another advantage is that we can now have some information on this intermediate depth of soil moisture. Because we have the model, we can infer some information for that. And what you saw here in this time lapse was actually also this root zone soil moisture for up to 1 meter of depth. Of course, for models, we know that they are not always correct. They strongly depend on the input data. In our case, it's rainfall that might be erroneous. Also, models, their setup might be a bit wrong. And so what we ideally then would like to do is to actually merge these complete model results with the satellite observations that we have at hand. And this process is called data assimilation. So what we then do is we have the model simulations for all the layers of the soil, and then we use the information from the satellites to update those predictions or model results. For SMOS, then that would be that we update the upper surface soil moisture, and with the GRACE information, we correct the total water storage. And you can do that individually, or you can do that both at the same time. And of course, corrections in the model will then in turn affect all the other layers in the soil or all other parameters that are predicted, to then overall paint a much more realistic or accurate picture. And that this process is in general very positive and leads to more accurate results. It has been proven for the general process of data assimilation. Now we're the first ones to actually look at this for landslides. To show you some examples, how can you imagine this data assimilation process? One example for a landslide in Canada, where we have in red here the model prediction. If we just have the pure model of catchment deficit, it's a variable that's proportional to the water table content, water table depth. So the closer to zero, the higher the water content. And what we see is that in the background, this is the GRACE observation. We see that from 1 month to the other, GRACE observes that there is higher water content in the soil. Our model didn't really see that at the beginning. But when we merge now, and this is now the green dashed line, the observations of the satellite with the model, we can actually retrieve a probably much more realistic result, because possibly at this time, there was some melt going on and GRACE covered that, but our model, because we only give a rainfall input, probably didn't see that. On the other hand, for surface soil moisture, this is now the time series here for a landslide in Colombia. In red, you have the model only representation or results, and the scatters on top here are SMOS observations. And what you see is at the beginning, they nicely agree, but then they deviate a bit. And when you merge now the observations of the satellite with the model, you create an intermediate value, I would say, that is probably more realistic, because it might really be that at this location, we had a rain event that wasn't covered by our rainfall input data. Is this now beneficial for landslide likelihood modeling? Well, if we assume that with higher soil moisture, we have a higher landslide likelihood, then we can say, well, data assimilation does not really help if we have already a very high or wet predicted soil moisture. If we already have very wet soil predicted by the model. But if we have, on the other hand, the model predicting very low soil moisture, and that would mean maybe a missed alert, if we base some predictions on this value, we can limit those missed alerts by using data assimilation processes. And we found this to be true for both SMOS and SMAP, so the surface soil moisture information, but also for grays for the total water column. And that's a bit, that's really nice to see, or also very striking, because grays, as I showed you, has this really large footprint. And there was still some information that we can infer from this, so that was nice to see. To summarize, well, we can say yes, both global land surface models and satellite observations have shortcomings. But models can help to get a spatially and temporally complete and also consistent idea of the soil conditions, especially also for remote areas. And we can prevent some missed alarms through the inclusion of satellite data, namely the process of data assimilation. I hope I could spark some interest or give you some more insight in something you didn't know before. You can read up on details of this in our recent publication in the Journal of Hydrometeorology. And at this point, also a big thanks again to my co-authors who immensely supported me. Thank
you. Thank you, Anne, for this presentation. It's very nice to see that using remote sensing at this scale, we still get information that is really relevant for our work, for our landslide early warning. I think this is not intuitive. I admit that I myself, I often had the impression that at this scale, we may not be successful to generate actually useful data for this local or regional landslide early warning, but your approach seems to be very interesting and going into the right direction. We will come back with questions later, and I would, before we go to the questions, move forward from remote sensing to the ground. And I would like to introduce Jim Whiteley, who is working at the British Geological Service. And he will say something about the added value of geophysical imaging for slope scale early warning systems. Thank you, Jim, for presenting this work.
Thanks very much, Manfred, and thank you everyone for tuning in today. Good morning or good afternoon, good evening, depending on where you're coming from. My name is Jim Whiteley. I work for the British Geological Survey as an engineering geophysicist, and I'd like to talk to you today about geophysical imaging for slope scale landslide early warning systems. I'll start by just briefly talking about why we use geophysical imaging for landslides, and then I'll talk about the more innovative aspects, given that we're in a session about innovations. I'll do that by talking about the Holland Hill Landslide Observatory, which is our test site in the UK, where I'll focus on some of the aspects and technologies that we've been developing specifically for the design, monitoring and forecasting of landslide early warning systems. And I'll then give a brief overview of the integrated approach we're trying to foster before looking at some of where the technologies are taking us in the future. So firstly, for those that aren't so familiar with geophysics, why do we use geophysical imaging for landslides? Well, McCann and Forster published a paper over 30 years ago now, identifying that there were three main aspects of a landslide that needed to be considered when it was being investigated, and that geophysics could really help with the investigation of. And that is the three-dimensional shape of the subsurface of the landslide, the definition of the hydrogeological regime, and the movement which is happening within or is caused by the landslide itself. And really in 30 years, we're still trying to achieve those things, but the innovation that we're applying here now is not just taking or using geophysics to get a snapshot of the landslide, it's applying some of these in a time-lapse or a monitoring sense to try and really get a better understanding of the dynamic processes that are happening within the subsurface. And geophysical imaging is great for this because it's both a rapid and non-intrusive means of doing that. And when we're using these monitoring techniques, we're able to acquire very high spatial and temporal resolution data from the subsurface of the landslide. Now, just thinking back to Anne's talk there, when you think about, you have these large scale or broader scale satellite observation techniques, which are looking at the surface. And then if you think about the other techniques that we use, things like sensor deployments or intrusive boreholes, which give you a very, very detailed information from the landslide, but in a very small area, we really see geophysics as the kind of bridge that takes us from looking at the very large scale to the very small scale and considering lots of these processes that happen within the subsurface of the landslide. And we can do that using these imaging capabilities of tomographic geophysical techniques. Where the challenges lie are in the non-uniqueness of geophysics. So the models that we get from our geophysical observations can have many different solutions. And that's a question of uncertainty, which we can try to address by using multiple methods. And also, these measurements were taking very much proxies for true ground conditions. So something we need to consider is that the measurement we're observing is not always directly related to the property that we are trying to investigate. I wanted to try and put this within an early warning system framework. So I chose the early warning system framework put forward by Emanuele Intrieri and his colleagues in natural hazards and earth system science, and just wanted to discuss a bit about how our geophysical systems can help with these areas. So particularly in terms of design, how we can use geophysics to map the subsurface of the landslide from a reconnaissance perspective to have a better understanding of the geological knowledge and how that landslide works. The monitoring is where the main innovations lie. So that's the recent developments in autonomous instrumentation and data collection and transmission of 4-dimensional subsurface models, which can tell us about these dynamic processes. And also in terms of elaboration, taking that geophysical data and trying to present it in a way which is not just meant for geophysicists, but meant for a wide range of people who can use that to better understand these processes. That also ties into forecasting. So once we've taken this geophysical data and started considering it within perhaps engineering or geotechnical terms, we can start to look at comparing the information with thresholds, or trying to work out what a landslide is doing or perhaps not doing in relation to external environmental factors. And finally, although I'm not going to talk about education in this talk, it's important to think, I mean, a picture can often say 1,000 words. And what we do have in geophysics are some very, very pretty pictures of the subsurface, which is a great way to try and get our message out to people who don't have a good, strong background in earth sciences. So our test site, the Holland Hill Landslide Observatory, is a very slow-moving landslide driven by increases in ground saturation located in North Yorkshire in the United Kingdom. And it basically is a large hillside, mostly comprised of a sandstone, which is very porous and quite stable. And overlying the sandstone is a very plastic, a very unstable mudstone called the Whitley Mudstone Formation, which fails when it gets to a particular moisture content. And you can see in the bottom left here the kind of development of the back scarp rotation and various plastic flow lobes over the course of a decade. And interestingly, we can see that if we just look at rainfall alone, there isn't actually a very strong relationship between movement and just large rainfall events. What we really have to get this landslide going is antecedent ground saturation. And again, this is an important thing that geophysics can provide. It's not just looking at the relationship between what rain is falling on the landslide and whether it's moving. It's to try and work out the understanding of what that water is doing inside the landslide and how that's affecting the landslide system. In terms of early warning systems designs, we can use geophysical methods to kind of create reconnaissance maps of the landslide subsurface. So on the left here is an example using just a 3-dimensional resistivity survey, where we can identify the Whitley Mudstone as a very low resistivity, very saturated unit in the blue there, and then the Staith Sandstone as a high resistivity, so porous and dry unit underlying that. We can see where the Whitley Mudstone is failing over the top of that stable unit. And perhaps something a little bit more advanced, we can start to use things like machine learning and clustering approaches to try and take multiple geophysical data sets and try and come up with a ground model just based on those. So on the top right here, we have a detailed ground model that's been developed from various geotechnical, geodetic, and geophysical surveys over many years. On the bottom right here, we have a model that was created using machine learning, where we just try to identify the main lithological properties from the geophysical information. And this took a fraction of the time to create compared to the very detailed information model that we have on the top there. In terms of landslide early warning system monitoring, we've been developing an autonomous remote geoelectrical monitoring system, which we call PRIME. And this is a geoelectrical system that sits in a cabinet and can be deployed autonomously to a landslide or to any kind of embankment or slope which needs monitoring. And we're able to collect data via telemetry on that system to bring back to the office and have a look at, and it tells us what's happening with the landslide over time. So we can use things like time-lapse images. This on the left here is a time-lapse image of electrical resistivity tomography, which is showing us as we go through the year into increasing blues, the saturation that's happening in that mudstone unit. And on the right here, this is some of the research I've been doing, trying to integrate seismic methods into this. So this is actually using repeat active seismics, which are far more sensitive to the stress state of the landslide, whereas the resistivity tends to focus on changes in moisture content. And more importantly, I think perhaps the most important thing here is, as I said at the beginning, We use this data as geophysicists to understand the subsurface properties of the landslides, but we feel we have a duty to try and bring that information to people who maybe aren't so well versed in geophysics, and to try and bring it to the community so they can use it in their early warning systems. And here on the left, we just have a petrophysical relationship that's been developed in the laboratory between resistivity and moisture content. And what that means is we can transform our geophysical measurements into something which is far more useful. This is now a map of moisture content in 3 dimensions. And when we start using our time-lapse imaging and monitoring systems, we can start to get 4-dimensional maps of where the moisture is moving within that landslide, to try and help us mitigate risk within particular areas, and to try and put our landslide prevention strategies in place. So we've tried to apply this to our prime monitoring system, and this again is just highlighting where we see the main areas of that landslide early warning system applying to what we do. So whether it's in the field measurements and deployment, the data transfer, the automated data processing, and then the delivery of that information to our clients. And on the right here, this is just a recent example where we've installed one of our prime systems into an active railway embankment, which is failing. This is actually a landslide here, just on the base there. So it is starting to be used by stakeholders in some of their landslide monitoring and mitigation strategies. Just very briefly looking at the future, geophysical monitoring is being increasingly used to try and investigate landslides and to monitor them. This is from a review that we did a couple of years ago, just showing that throughout time, we've had a much bigger increase in terms of the amount of data we're collecting. So we're monitoring for longer and longer, and the size of the dots there relates to the number of data sets we're acquiring, and that we are increasingly getting more and more data from the landslides. And this is something that's only going to increase with the kind of advent of distributed and nodal systems, particularly in the field of seismics, where we've already seen in other applications, we're able to collect huge amounts of data from almost continuous distributed systems. And this is something we've recently installed onto our landslide at Holland Hill. And we're having some quite exciting results coming out of that at the moment, where we're able to see strains developing after we've mapped the developments of moisture content accrual in particular areas of the landslide. So with that, I appreciate we've covered a lot of ground in hopefully what was 10 minutes. But if you have any further questions, I think we're going to address them at the end of this session. But also, please do get in touch. And there's just a list of references there. Hopefully that will be made accessible after the session. But thank you very much.
Thank you, Jim. Perfect in time. Thank you very much. And it was a very nice compliment, I would say, to the first presentation of Anne, I would say. Also with regard to this comment of the bridging scale here, which we also have had discussions about it. And I was also very pleased to see that your comment, to hear your comment about the added value for knowing the antecedent moisture rather than the saturation increase during the event. That compares very well with our experiences as well here in Switzerland. Thank you very much. We will come back with questions later. But before that, we go now to the topic of precipitation. And here I welcome Ascanio Rossi from University of Florence in Italy. You will tell us something about how this more traditional way of using thresholds, rainfall thresholds, how that could be advanced. And here we hear something about 3D rainfall thresholds. Thank you very much.
Thank you, Manfred. Good day to everyone. I hope you can hear me clearly. So my name is Ascanio Rossi. I'm a geologist. I'm a researcher at the University of Florence. I'm going to present the work that we made with my colleague to define some three-dimensional rainfall thresholds to be used in operational landslide early warning system. So just a small overview. This work was made in the framework of a project where we were requested to create a model to be used to implement an operational regional landslide warning system. Our model has to agree with some requirements. In particular, it must be simple to use and to understand by the operators. It must be based on easily accessible and constantly updatable data. And most important, it must be reliable. So it it must provide a low number of false alarm, and also we were asked to define 4 warning levels. So this work was made in Emilia-Romagna region, is in Italy, northern part of Italy. You can see all these red dots. There are a lot of landslides in this area that are mainly in the southern part, that is most mountainous part, and it is also the most rainy part of the region. It's a quite heterogeneous region with a quite heterogeneous territory. How we made the threshold? So we started with a very simple model, intensity duration model. We have to work simply, and we start very simply, but we did not define a single threshold for the whole region I used in the literature. But according to a procedure that we made some years ago, the region is divided in 8 zones named alert zone. Each one is characterized by its specific natural hazard. And for each one of them, we collected rain data, landslide reports. In total, we had over 1,000 landslide reports from 2005 to 2019. And for each of them, we define a set of thresholds. How we made it is we used the software named Macumba that we developed some years ago. You can find here a small reference that allow a fast analysis of this huge amount of data, and also allow to define a threshold according to the intensity, duration, power law defined by Kane. And the most important, it allows to define some rule to identify a rain event. This is important for the operational part. Each threshold that we defined was used, underwent quality control. So we checked the number of correct alarm, the dots in this plot, the false alarm, and also the missed alarms. As you can see here, we have 4 warning levels, so three thresholds and 4 warning levels. This model, yes, is simple. It makes use of easily accessible, constantly updated data. Use only rain data, but it was not completely reliable. Why? Because we had a lot of false alarm. Here you can see we have over 100 false alarm, less than 90 correct alarms. So we had to improve this model. And in this area, in a previous study that we made some years ago, we noticed that soil water content is an important parameter in landslide triggering, but this parameter, soil water content, is not easily accessible and is not constantly updated. So we continue to use rainfall data, and we define a new parameter that we named mean antecedent rainfall, or MEAR. We defined it as the mean rainfall recorded from all the rain gauges of a given area over a given time interval. It is something different from the classical concept of antecedent rainfall as from Aleotti in 2004 that defined from landslide, defined the critical rainfall, and then the antecedent rainfall as the one before the critical rainfall. Our mean antecedent rainfall encompasses all this time, so from the landslide up to 7, 10, 15, or 30 days, that are the time interval we tested. We calculated this value for all the events that overcome the first threshold, the threshold 1, that you can see here. It's the same of the previous plot. But in this case, along with intensity and duration, we added in this case, 30 days mean antecedent rainfall. And it's quite clear that yellow dots are false alarm, red dots are correct alarms. It's quite clear there is a difference. And in the frontal view of this graph, this difference is even more clear. So correct alarms 100 millimeters of rainfall. False alarms usually have values lower than 100, also lower than 60 millimeters of rain. How we use this information? We created a new threshold. As you can see, this plane is threshold, so a threshold based on long-term rainfall. And in this way, we coupled intensity duration threshold, that is this shaded plane, with the mere threshold, the green plane. So we were able to reduce the space associated with the landslide triggering. In traditional analysis based only on intensity duration, the shaded plane, everything that is on the right of this plane is a rainfall condition associated with the landslide triggering. In this way, we reduced this space, so we had a better description of the rainfall condition associated with landslide triggering. And how it worked, we made some tests with 4 time intervals in 6 different areas, and we noticed that our approach helped us to reduce the number of false alarm from 30% up to 70%. Then we made this analysis using 2 different data sets, calibration data set of 10 years, and then we validated this result with the other 2 years of landslide, and we saw that the results are quite consistent between these 2 data sets. So we used everything to create a warning system that is not only warnings. We have the warning level for each rain gauge, we have the rain path of each rain gauge, but we have also a little bit of forecasting. And also all this data from every rain gauge are aggregated after a second step to a scale of alert zone. So in conclusion, what we noticed that the combined use of long and short duration of rainfall can help to improve the performances of our warning system. In this area, we noticed that also shallow landslide seems to be influenced by long rain events. And also, since we use the mean rainfall of each area, landslide, this means that landslide are triggered by more widespread meteorological event than isolated rainstorm. And last step is also an invitation for everyone. We need further analysis in other zones and other areas to understand if our approach is valid also in different conditions. And this is if someone wants to read the paper.
Thank you very much, Ascanio, for this presentation showing that there is still possibilities for advancement using precipitation measurements alone. And you showed with your method a new way to find even better thresholds. And I see a lot of potential here for early warning services who actually are very used to use this precipitation methods, but I see that you can contribute and that there still is potential for advancement in this field. I will come back again with the questions later, and I ask everybody who is listening here to ask your questions either to Anne, to Jim, or to Ascanio into the chat, and then I will come back to these questions later. But before that, I would like to give the word to Fabian Walter from Switzerland, from my institute, who is a specialist in using data from seismic data for the purpose of early warning. And he will tell us something about his work and his innovative approaches.
Thank you very much, Manfred, for the introduction. I assume you can see my screen?
Yeah.
Yes. Okay, then I'll start. Yeah, I will address the question if modern algorithms, artificial intelligence, machine learning, and so on can actually help us warn against destructive mass movements. And I would like to acknowledge my co-authors right here, especially Małgorzata Chmiel, who was really the postdoc behind the study. And I will mostly focus on the torrent, the Swiss torrent of Ilgraben, which you see in the background right here, which is a prominent debris flow channel in the European Alps. So here's another picture of the Ilgraben. You see on the left hand side a panoramic view. And what's special about this channel is that it carries several debris flow events per year. Without going into much detail, you can imagine that this is very nicely suited for research purposes. We see the traditional or the typical hazard chain, the cascade. We have strong erosion from the lateral sides of this canyon, the steep sides, which then accumulate sediments in the bed of the channel. And later on, these sediments are mobilized in forms of debris flows, such as I just showed before, or I'm showing you right here in this movie. Now, in the lower part of the Ilgraben channel, which is in this inhabited part of the Rhone Valley, as you can see right here, there's actually a lot of early warning technology already implemented, very reliable. What is still not implemented is a way to monitor also the upper catchment. And you can imagine that if we see the upper catchment somehow in our early warning technology, then we can significantly increase warning capabilities and warning times for our alarms. And both of these two, if you divide roughly the channel into two parts, both of them are about 2.5 kilometers long. So you can see how much of a gain we would get if we can really detect events up here where instrumentation is not really feasible because the terrain is very inaccessible. So to tackle this challenge, we decided to use seismometers. We installed sensors throughout the Ilgraben catchment. I'm showing you some right here by the white triangles. We record very nice debris flow signals. Again, I don't want to go into details right here, but what's important to take away is that these are very clear seismograms lasting for tens of minutes or even an hour. And you can see how they move through the network right here. This is the instrumentation, very compact, very easily deployable, and also this we can dismantle it very simply. So a human observer could very easily identify these kind of signals, even if he or she is not an expert. But of course, it's not possible to stare at a screen at streaming data for 24 hours a day and then trying to identify incoming debris flows. So the idea is to use machine learning to pass this task to a computer who can do this around the clock with a similar reliability as humans. And what I would like to show you in our talk is how we implemented such algorithms, especially how we implemented them to produce these kind of plots right here, where we have time of the day on the x-axis, the time in the summer on the y-axis, and we want to continuously classify our seismic signals. If they are noise not of interest, then they have this skin color right here. If they are related to debris flows, different phases, then they have these greenish or bluish colors. So another word on Ilgraben. Here you see another picture. Again, we have lots of implemented warning tools in the lower part of the Ilgraben, but our network looks like this. And you can see that the debris flows are actually quite variable. So we have to make sure that we train our algorithms to not only catch very watery events, for example, but also those which are particularly destructive with large boulders. So again, this is how one of those debris flow seismograms looks like. And we're partitioning our seismograms into a pre and post check them one phase. We know from alternative instrumentation when the debris flow crosses this check dam right here. And we are interested in particular in the time before this crossing. Down here, this is something that can be captured with existing instrumentation, but we're interested in this part right here. So in the blue part of the seismogram. So we're dividing everything into these, all debris flow signals that we have recorded in the past into these 2 time windows. And then also we create a noise class right here. And from the 22 debris flows that we recorded between 2017 and 2019, we had quite a bit of time windows for these classes. We have nearly 50,000 noise signals that we can use, over 10,000 of post-check M1 signals, and at least a few thousand pre-check M1 signals. So rather than trying to train an algorithm that catches really a debris flow signal, what we will do is we will classify 100-second long windows. You see the scale right here, and try to classify it into whether they belong to a debris pre-check M1 debris flow signal or a post-check M1 debris flow signal. The way this is done in machine learning, these tasks, you translate your signal into what is called a feature. So for example, one feature could be how much energy is in the signal, how strong are the amplitudes, what is the median of the absolute value of the amplitude, and so on. And this is something then that a machine learning algorithm can handle well. So again, I won't go into details, but they're specified in the paper that was recently published on this work. Then in this slide right here, sorry, you see first of all the algorithm that we're using, signified by this sketch, by this flowchart right here. This is what is called a random forest algorithm. It asks successively yes or no questions. So for example, is an amplitude larger than X or smaller than X? And if you, depending on what the answer is, you ask a subsequent question, and you ascend into these decision trees. And with these decision trees, the algorithm can actually learn how a general debris flow signal looks like. You're not really you're not teaching it how this particular event that you're showing to the algorithm looks like, but how the general features of debris flow signals look like. And of course, the larger the training data, the more accurately the algorithm will learn. On the right side, I'm showing you what is called the confusion matrix. So this is a measure how well these machine learning algorithms work. On the Y side, on the Y-axis, you have the true label, so what we know we're giving the machine. On the X-axis, you have the predicted label. So ideally, we want all predictions to be exactly the true label. So ideally, everything should be 1 on the X-axis, but there can be some degree of confusion, which are the off-axis elements. You see that for the late debris flow signals, we're actually doing quite well, 94%, also for the noise. The early debris flow signals are a little bit worse. They're also getting confused most, as you can see in this in the right top corner. But this is because they're very close to the noise signals themselves, because this is really the earliest part of the debris flow. But in the bottom, you see that if we apply some extra conditions, such as successive alarms for the pre-check M1 and post-check M1 phases, then we can actually increase the success rate beyond these on diagonal elements. So this was perhaps a bit abstract, so I want to show you how this looks in real life. We tested this approach last year, where we were lucky to actually observe 13 torrential events, a lot of debris flows, but also sediment transporting floods. And in the panel below, you see again this figure with the time of the day on the X-axis and the Julian day during that summer on the Y-axis. And you can see most signals are classified as noise, as we would hope, but we see the debris flow signals, which are these worm-like features with the blue heads. So the early debris flow pre-check M1 detections, and the post-check M1 detections in green. And for this year, actually, our algorithm detected all 13 torrential events with not a single missed or event, or not a single false alarm. You can see right here how this looks like, especially if you look at the blue right here on the top bar, the color bar on the blue detections, the pre-checked M1 detections. For some stations, really, the algorithm somehow figured out a way to detect the signal as soon as the seismic signal emerged from the background noise. So really the weakest parts, the earliest steps of a debris flow. And the early warning times were actually quite encouraging. These are the warning times with respect to the arrival down in the valley at the Cantonal Road. And sometimes we actually exceeded more than 2 hours for the early detection time. So this brings me to the summary. I think with enough training data, we're really at the point where we can use real-time seismic data to warn against debris flows using machine learning algorithms. And this outperforms existing technologies if we have access to enough seismic stations. There are some important questions that are remaining. The first one is, can we predict the size of the debris flow? Because we don't want to warn against a small debris flow or a torrential flood if it doesn't cause any destruction. And for this, I think we have an answer sort of already. Here I'm showing you the seismic signals at 4 stations on the y-axis that were recorded when the debris flow cross-checked M1, and on the x-axis I'm showing you the measure for the impact forces within the debris flow front when it reaches the end of the torrent, so the Cantonal Road. And this latter measure is a measure for how destructive the event is, because the larger the impact forces, the more large sediment sizes, so the more large boulders are in the flow. And you can see that there's actually a rough scaling. So for some stations, we can use the early detections to predict how destructive the event will be once it reaches the valley. The second question, which is probably more important or more challenging to address, is can we transfer this approach to torrents where we do not have the amount of training data? And this is something we're working on right now. Thank you.
Thank you very much, Fabian, for this, again, very interesting talk. Certainly we see here that with this method, you are at the front of groundbreaking innovations. And I would like to thank all 4 of you for these insights that you gave from your topics. I would like to follow up with a few questions only. We don't have too much time, but I also ask you to answer these questions that were asked in the chat, that you could maybe answer them in writing later on. But here, first question to Anne that I see was asked from Nikhil. He asks about how are the uncertainties arising in your method from the use of this large spatial resolution of grays accounted for within the catchment scale model.
So Grace actually has a very, very precise measurement in the water column of centimeter scale. So that's like, because we have such a coarse spatial resolution, it's finer in that height amount kind of. And actually in this process of data assimilation, there is accounted for the uncertainties of both the observation that we have, but that's a static error or uncertainty that we assign to it. And then on the other hand, we have our models, and actually it's not just one simulation of the model, it's an ensemble. And therefore we know how certain is the model with its predictions, and then we can kind of do a weighted average. So if we know that our observation is really uncertain, then we will not give it as much weight. So in that sense, we do account for, like, this data assimilation process assures us that we kind of account for this uncertainty.
Okay. Another question goes to Jim with regard to your geophysical measurements that you did. You mentioned that you were able to detect antecedent moisture, but did you find the location of this highest soil moisture concentration in the slope? And is this in some way indicative for the intensity of the movement?
So yeah, we haven't actually looked at what the kind of magnitude of the moisture content has in relation, or what it means in relation to the movement itself. The main thing was, because this is a very heterogeneous landslide, we were trying to locate where the moistures were developing. That was the main aim of trying to use this resistivity approach. But what we were able to do was establish almost like a subsurface moisture content threshold, at which we were fairly confident that we would see failure, and that was 48% in terms of gravimetric moisture content. So we knew from then on that when we started to get towards 48% gravimetric moisture content, we were very likely to see failures in the slope. And another thing we noticed as well was that those failures, again, because we're doing long-term monitoring, happen in different parts of the landslide depending on which parts have failed previously. So it's actually that the slip surface in the middle of the landslide is the area that's wetting up. And that's actually the part that fails first. So you have this plastic deformation in the middle of the landslide. As that removes its support for the overlying area, that's when you get the rotational developments of the backscarp in those areas. And then actually that starts to push down on the whole landslide, which is when it starts to fail across. So it kind of indicated the kind of the very complicated processes that are happening as a result of this very heterogeneous environment. But it would be really interesting to look at whether the magnitude of the soil moisture content has some sort of relationship to the intensity or the maximum displacement we observe. Okay,
thank you very much. We also have a question here with regard to this 3D threshold to Ascanio Rossi. There was this question about these secondary thresholds, if they are constant or non-constant thresholds.
Yeah, so the secondary, the second and third threshold are constant as the first one, and also the threshold based on descent and rainfall are constant inside each zone, but they can change from zone to another. For machine learning, we are still trying to do something, but it's not easy task, mainly because of the time. Because machine learning need time to create the model, but also for its application. And this warning system we made is a fast updating system. So sometimes the time to collect the data, process them, and to get the output is more time than the update time. So we are trying to do something, but we are working on it.
Okay, thank you very much. There was a question about the sensors that you are using, Fabian. Somebody wanted to ask what kind of seismometers are you using in these studies that you presented from the Ilgraben?
We're using 1 Hertz Lennart's seismometers. This is a standard seismometer, and it seems that really you have to go down to 1 Hertz for this study. Using geophones with higher frequency ranges above 4.5 Hertz or 8 Hertz, as they're often used, seems to miss important parts of the signal.
I'm sure there are many more questions, and I welcome everybody to put your to send your questions by email to the speakers of today. I would like to thank again all of you, and I would end this session here by telling you that there will be another session on innovations early morning tomorrow, at least here in Europe. And you are, of course, welcome to hear what the users of these new methods will say about these innovative methods, how they can use innovative ideas and new methods. With that, I hand back to Anne, and thank you very much for joining this past session on innovations.
Thank you, Manfred. I think we'll have a 4-minute break, and then we'll be back with the next session.